everyone. As we have long been waiting for this seminar, Dr. Vicedo-Cabrera will talk about the most advanced sciences in how to attribute the health impacts to climate change. Vicedo-Cabrera's current research develops along the intersection of epidemiology and climate sciences to understand how different climate factors and other related environmental stressors affect health in the context of climate change. So she has many excellent publications in the climate epidemiological field, including using the multi-country, multi-city network data to look at the health effects of ozone and the health effects of heat-related mortality, including the one study that she will be mainly focused on today. But before we hand over to Dr. Vicedo-Cabrera, I want to just mention that how's the community role that if you do have any questions, especially our online audience, please feel free to type in your question in the chat box, and we will have all the questions answered at last. So thank you, and without further ado, Anna.
So just give me a second. Sorry. Do you hear me?
Yeah, very good.
Yeah, perfect. So, well, welcome everybody, and thank you very much for being here in this webinar. And of course, thanks a lot for the invitation to contribute to this event today. It's a great pleasure for me being here to talk about a topic that, in a way, has been a bit of my nightmare, I must say, or a bit of my priority during the last, I would say, 2-3 years. And I believe that it might be one of my main research fields in the coming years as well. So I hope that basically at the end of my presentation, you might have some already some insights about this topic, and probably you might get inspired as well about this specific topic of attribution. So you will see, as you could see from the title, we talk about attribution of health impacts to climate change, and you will see that mostly of my presentation will be focused on heat and health as an example. So let's start from the very beginning. See if I can. Okay. Yeah. So basically, heat is considered nowadays an important environmental stressor. Very recently, it was estimated that around 1% of all deaths globally can be attributed to heat. That translates around 7 deaths per 100,000 population per year. And as well, it has been estimated an increase in morbidity, in particular for cardiovascular, respiratory, and mental disorders. And as well, it has been identified several, let's say, vulnerability populations, such as elderly, pregnant women, chronic patients, and children. And finally, has been estimated an important burden in terms of economic cost and also reduction in labor productivity. So everything all this taken together is considered that heat is an important element to be assessed in our field of climate change epidemiology, in particular with regards, let's say, climate change research and the next, what is going to happen in the next decade. So let's say that we, let's say how heat affects health. In a way, we can see that first, the mechanisms by which heat directly impacts human health are complex, and understanding, let's say, how the body reacts to heat has been the focus of decades of research in different fields, in particular in physiology. Heat stress is kind of the overarching term that is used for, let's say, to describe the response of human body to the exposure to heat, and usually happens when the body is overwhelmed by metabolic heat production. You can see here from this diagram, basically, our body, what it has to do is kind of react to the exposure to heat in several mechanisms to try to dissipate, or let's say, emit the overheating that we have in our body. And if in a way, if this is not efficient, what it can create, or let's say can cause or trigger different mechanisms that eventually can damage different systems or organs in the body. In this nice review that was recently published, they summarize most of the evidence of the different mechanisms, and they have seen that actually there are several, let's say, several organs that are directly affected by heat exposure through different mechanisms, such as ischemia, heat cytotoxicity, inflammation, etc. This is from, let's say, physiological, more mechanism point of view. But if we, let's say, as epidemiologists working on climate change research, we know that we assess heat in a kind of different way. Basically, what we do is to have our wonderful, or let's say, so-called exposure response functions that in a way summarizes the association between the ambient temperature, in this case, we focus on heat, and a specific health outcome, that is, in this case, mortality. That basically you see here in the y-axis is the relative risk, and in the x-axis is the temperature. In this case, it's representing this, let's say, association that usually is non-linear for the CTOM ROM, and how we define heat is basically all temperatures above a specific threshold that we call temperature of minimum mortality, that is directly defined from the curve that corresponds to the temperature for which the risk of dying is minimum. So every temperature above this threshold is considered heat. And we know that risk increases steeply from this point onwards, as you could see here in the curve, up to a maximum. So basically, this is how we assess heat, the effect of heat on health. But to make our life a little bit more complicated, we know that actually the effect of heat is very different across locations. I mean, we can assess this exposure response function or curve from a specific population, but we know that we cannot extrapolate this curve to other locations, because we know that vulnerability is very specific, very particular for a specific location. It's mostly because of the different combination of, let's say, factors or vulnerability factors or resiliency factors that make this population more or less resilient to non-ambient temperature, in this case, for heat. So in a way, you could see that during the last years, there has been a lot of, let's say, developments in the field of climate change epidemiology and try to clarify how heat affects health. But if we have to define specific moments in time in the past that in a way constitute an important, let's say, kind of turning points, how we assess the effect of temperature on health, in more particular on public health, is this event that happened in Europe in 2003, is this massive European 2003 heat wave that was that affected very heavily Central Europe and the southeast of Europe, in the Mediterranean area. And basically what happened is that it was so massive, so unique, that made that everybody turn their, let's say, focus, in particular on public health, on heat. Actually, a few years after that, there was an assessment in which they estimated that actually around 7,000 deaths could happen during this massive event. So in a way, it gave a kind of very clear idea about the severity of the event. And more importantly, what was at that time is really to say, okay, if this is happening now, what would happen in the future if we know that probably due to climate change, these events will be much more frequent. So while epidemiologists, let's say, as we were assessing what were the impacts of that event at that time, in particular, try to understand how we can implement public health measures, how we can protect population from future events, climate science community, they were more thinking, okay, and what could have, in a way, what was the role of climate change in this event? In a way, there's this kind of not very good question, or let's say an ill-posed question, whether this 2003 heat wave was actually caused, in a very simplistic or the deterministic sense by a modification of external influences on climate. Basically, as we said, due to the increase in concentration of greenhouse gases in the atmosphere, because we know that almost any such weather event might have occurred by chance in a world without climate change. In a way, what we have to do is to think it in another perspective, or let's say to put the question in a different way. Basically, is how much did human activities increase the risk of occurrence or probability of this event? Or more specifically, did actually climate change alter the severity, frequency, or duration of the event? So this is exactly what attribution and detection studies does. It's a field that it has been in a way developed during the last years, in a way it's more traditional for the climate science community, but not much on the epidemiological side. In a way, one of the first examples was actually this study led by Peter Stott from the UK, in which actually they assessed what happened in this 2003 heat wave, and where they came up from this study is that it is very likely that human influence has at least doubled the risk of a heat wave exceeding this threshold magnitude. So in a way, it's already putting like a surname into this event, saying that probably climate change have altered the, let's say, probability of the occurrence of this event. So how these attribution and detection studies work? So basically, it's in a very simplistic way. What happens is that we model, let's say, we compare our current climate in presence of climate change that we can actually, in a way, estimate or let's say mimic or get simulations based on this kind of climate models in which they kind of try to mimic current conditions based on what we know in terms of greenhouse gas emissions. And we compare it with a world without climate change. So basically is what you can see here. We compare, here is in this graphic that is a kind of simulated data just for you to illustrate this comparison, in which we have our warming climate that is increasing in red compared to a kind of climate change free environment, or what they call a naturalized scenario, or let's say without anthropogenic forcings. So in a way, the difference between these two scenarios would give us what is actually the contribution of anthropogenic forcings. That eventually is what we want to know. What is the human influence in the climate that actually might have altered the climate in current, let's say, current period or historically during the last decades. So as I said, it's a field that has been developed during the last years, in particular for the part of the statistics, because of course we know what is happening now. I mean, we can see whether these simulations from these climate models really mimic what we are experiencing today based on observations, but we don't have data what would have been the world without climate change. So in a way, we have to rely on these models that eventually when you reduce these, let's say, forcing, so there's these inputs in your model, you are actually mimicking what would have been the world without climate change. So in a way, you can see that there are a lot of uncertainties. And of course, one thing that I would like you to put in your forefront is that when we talk about attribution and detection studies, we talk about basically probability. This is a term that you will see that it's very pivotal in all this story, because in a way, it's not a matter of, okay, yes or no, climate change have caused this event. It's whether climate change has altered the probability of this event. So basically what let's say people working or researchers working in climate science, mostly on the part of attribution and detection studies, what they do is to compare probabilities, as you could see here in red, the probability of an event happening above a specific temperature threshold compared to the same, let's say, threshold, what would have been the probability in a world without climate change in this counterfactual scenario. So as some, let's say, in this nice review, this researcher, Freddie Otto from Oxford, she very well described in this paper, in this review, in which basically what she said is that out of this exercise, we could have 4 different outcomes. First, could have been made, let's say that this event could have been made more likely because of the anthropogenic climate change, let's say, or it could have been made, let's say, less likely, or there is no detectable influence from anthropogenic climate change. And the last one, with our current understanding and available tools, we are unable to analyze the world of external drivers in this event. So basically, as you could see, is to see whether climate change altered the probability to make this more or less likely. And if we have enough resources, or let's say our models can help us to really clarify whether this difference in probability is meaningful. So to understand this word of attribution is we have to talk about, and usually you will see this plot in every study in this field. For us epidemiologists, is basically something that we, I mean, honestly, when I saw it, I say, I don't know what the hell is this, but at some point I found it very, very interesting. So I will try to guide you through this plot. You could see here in the y-axis is the monthly temperature equivalent. And in the, basically in the x-axis, you have what they call return time. It's a measure of, let's say, of probability or severity of an event. It's basically, you put here in this point, what it's saying is that an event has a return time of 10, or basically that it happens 1 in 10 years. If you go in here, it's an event happening 1 in 100 years. So in a way, you could understand that the far you are from the origin, the more extreme an event could be, or the less likely, as you could see here on the other side of the axis, less probable an event is. So basically what they do, in this case, is an example of the 2010 heat wave in Russia. And it's basically to compare this blue line that in a way is used based on this counterfactual word, in which you have basically, this is the probability of a specific, let's say, event happening at different times. And in red, the same, but in our currently, in our, let's say, in our current conditions of global warming. So just to, if you go in this line, along this line, it basically corresponds to this, this threshold that was, let's say, defined during this heat wave. But basically this heat wave reached, I think it was 24.5 degrees. So in a way, according to these estimations, what they say is that in current times, this event corresponds to approximately 1 in 50 years event, while in a world without climate change, this event would have corresponded to a 1 in 100 years. So basically what has happened is that climate change has made the event more likely, let's say, from an event in an hypothetical world of 1 in 100 years has become 1 in 50 years. So as you could see, again, is the idea of changes in probability, making a specific event or a specific temperature threshold, make it more probable, let's say, going from 1,100 to 150 years. So as you could see, it's a kind of, you know, something that is not very, for us as epidemiologists, it's a little bit difficult because in a way, it's just talking about probabilities, but for us, translating this into health impacts, it requires a bit of work. But let's say that we are working on it. The idea is that this word of attribution has gained kind of a lot of attention during the last years. In particular, thinking about what happened this last summer, surely you might have heard or even lived or suffered this event, this massive heat wave that happened in last summer in West Northern America. So in a way, what happened, we know there were a few days with temperatures above record, and it was a lot of attention in media, etc. So while all this was happening, let's say that there was an initiative from this World Weather Attribution Initiative that it's a kind of, again, it's an initiative in which different researchers working on attribution studies put together and try to give answers about whether climate change might have had some role in a specific extreme weather events. Not saying that to provide this evidence a year or 2 years after, is really to provide this evidence in the coming weeks, because we know that times matter. If we have suffered a heat wave like this, it would have much more impact if this answer comes earlier in time rather than years ahead, that people might completely forget about the severity of this event. So the idea is that this group of researchers undertook this analysis, and basically what they came up with is that it would be virtually impossible without human-induced climate change, that this event is estimated to be about 1 in 1,000-year event in today's climate. So you can have from this sentence that this event was kind of unique, very extreme, 1 in 1,000 year. It's a lot. And actually they provided this plot. You will see that it's very similar to what I just shown. And actually this event that was in here around almost 40 degrees, they saw that it was actually even outside the probable range of events within a year, let's say in our current climate. So in a way, it's saying already about this huge severity of this event that happened. So this study and this evidence they provided at this time, that as I said, it was a couple of weeks after the event, was very, very powerful, because it's giving clear, let's say, putting the finger into the idea of the role of climate change and the human influence in this event. So the message was very, very, very strong. At the same time, we have to bear in mind, actually, you know, that there was this, the new report of the IPCC, the part on the physical science basis was already published in August. And in the difference, let's say, of this report compared to previous reports, really to put in more weight into the influence of the human activities on current, let's say, extreme weather events happening in today's world. So again, you can see that the idea of attribution is gaining much more attention lately, but more importantly, because we know that evidence from attribution studies can be used in lawsuits. Basically, it has been used for specific, let's say, companies, individuals, etc., to kind of give some complaints, or let's say to ask for some compensations of specific losses to, let's say, governments or companies emitting greenhouse gases. So the idea is that during the last years, it has been a tremendous increase in, let's say, different lawsuits that have been implemented against climate change using evidence from attribution and detection studies. In this plot, you can see that actually it was mostly during the second half of the previous decade that actually went super up. And most of these, let's say, these initiatives have happened in the US. More importantly, it's like, okay, we know that there's this tool, but we need robust scientific evidence that would help us to gain, or let's say to win these different, let's say, initiatives in the courts. At the same time, we know that, let's say that the idea of these initiatives is that beyond individual litigant, the idea is to seek to advance climate policies, drive behavioral shifts by key actors, and or create awareness and encourage public debate. So it goes beyond the idea of compensation. It's really to gain more weight, or let's say to put more emphasis on the role of climate change on the different, let's say, events, extreme weather events that are happening. At the same time, it's something that has been, in a way, highlighted as well, that nowadays is not an easy task. There are barriers such as access to justice, difficulties in dealing with scientific evidence, and the conservationism of many courts that eventually confronted the different policy issues. So in a way, the idea is that there's a lot of now research going on, putting together climate science and law, try to gain, or let's say to create some synergies that eventually would help advancing on this field on climate litigation. And one important, let's say, quote that I take from a recent publication of a colleague of mine, from Rupert Stuart Smith, they say that greater appreciation and exploitation of current methodologies in attribution science could address obstacles to causation and improve the prospects of litigation. So in a way, it's really saying, okay, we know that we can do something. Law can be a very good path for doing that, but probably as scientists, we need to, in a way, advance knowledge in this field and try to provide better, let's say, scientific evidence that would help, let's say, winning on these different initiatives in courts. So let's say that so far we have been working more on the part on climate events, more on the weather events, whether one weather event can be attributed, or let's say, how was the role of climate change. But what about health impacts? Okay, we know that one event might have been more frequent or more, let's say, the probability had increased because of climate change, but at some point we would like to know what this translates into health impacts. So as I said, the idea is how much of the observed health burden during an extreme event can be attributed to human activities, or more broadly, how much of the historical health burden of a climate-sensitive outcome can be attributed to climate change. So it's not an easy task. I mean, we know that in there might be some, kind of a lot of different, let's say, developments in terms of methods, etc. And actually, one example, for example, you know that I found this article in the New York Times that was basically, they showed some calculations based on a recent report of the CDC, based on the, let's say, what has happened in this massive heat wave in the Northwestern in the US. And actually, they just did a very simple estimation on the, let's say, estimated the number of deaths that were kind of excess, or let's say more than normal during that period of time during the heat wave, attributing that, let's say, that during this heat wave, more than 600 people died, because that in a way one could attribute to this heat wave. But the other question is how much actually of this burden can be attributed to human activities? Again, talking about the probabilities, not to say yes or no, is to how much of this burden can be kind of attributed to these events. So one of the first exercises that has been done in terms of attribution of health impact was this study published by Dan Mitchell, in which they assessed what was the impact of the 2003 heat wave in London and in Paris. And actually what they found is that anthropogenic climate change increased the risk of heat-related mortality in central Paris by 70% and by 20% in London. So eventually what is really in here is saying that how much human or anthropogenic climate change has altered the severity of this event, in terms of how much to really put a value, a number on these contributions in terms of health impacts. So in a way, you will see that it's clearly a different message compared to what I said before. It's not about the excess deaths during that period. It's really to say how many deaths can be attributed to anthropogenic climate change. So let's say that traditionally the way how we have assessed this is more into the future, comparing what has been the health burden attributed to heat in current times compared to what will be in the future using climate change scenarios, assuming that the difference between today and the future can be attributed to anthropogenic climate change. But you will see that from this idea of attribution studies is not about future, it's about present. Okay, this is something that you should bear in mind. It's really to use historical events and try to see what has been the footprint of human activities in historical events. So when we talk about attribution, as I said, one could focus on, let's say, on a specific event to say what they call event attribution for individual extreme weather events, as this example of Dan Mitchell. But another example is more on the trend attribution, basically for long-term changes in the middle of climatological statistics. Not really to assess specific events, is to see how much the observed trend can be attributed to human activities. So basically using this approach, not really to focus on extreme events, but on the trend during a period of time, is we did this analysis that it was, I had the pleasure to lead together with my colleagues of the Multi-Country, Multi-City Collaborative Research Network, was recently published this year. And this is the reason why I'm talking today about this topic, because thanks to this opportunity, I had the option to dig a bit into this topic. So in kind of general terms, this study, like the general framework, was about combining data and methods in epidemiology with modeled, let's say, climate projections, simulations of the past years. We were able to estimate how much of the observed heat-related mortality can be attributed to human-induced climate change. So I will go step by step. First, as I said, we use data from the Multi-Country, Multi-City Collaborative Research Network in 732 locations in 43 countries in the world. Here you can see the different location of the different places. And the idea is that we combine, let's say, we took all this data on observed temperature and mortality, and we derive these, the vulnerability functions or the exposure response functions of each city using the state-of-the-art methods in climate change epidemiology. Is basically two-stage time series analysis with distributed lag nonlinear models and multivariate multi-level meta-regression. Yeah, it sounds super fancy, but in a way it's not as complicated, and you have all the information on the method in the paper. I invite you to have a look if you would like to learn more about the methodological part. So basically what we did, as I said, is to estimate the vulnerability of each city, which in a way was already kind of an advancement compared to previous assessments, because again, here the idea is that we aim to assess the specific vulnerability of each population to have a better estimation of heat-related mortality in each location. And you see here that it was clearly heterogeneous. We saw, like, as we found in previous assessment, that actually most higher risks are usually found in Europe, in the Mediterranean area, and other locations in Asia. So as I said, we combine these exposure response curves with modeled climate data that we got from our colleagues from the EMIC project. This is the detection attribution model in the comparison project that is based on the last CMEP6 simulations. And the idea is that we, for each location in this assessment, we derive a series, let's say, of modeled or pairs of modeled climate or daily temperature under current conditions and under our without climate change. That is our counterfactorial scenario. Here you have an kind of illustration of the trends. Basically, in red, you have the observed trend with the warming trend, that it mimics current conditions with climate change, while the orange one mimics a world without climate change in the absence of warming. So basically, we focus on this period here between 1991 to 2006, 2018, actually, sorry about the numbers, I'm very bad with that. And basically what we did is, as I said, for each location, we obtained these pairs and we translated this observed, or let's say simulated temperature into hypothetical excess mortality under these two scenarios. And this is basically what you can see here in this panel A. In solid, you have the anthropogenic, let's say the heat-related mortality under current conditions, let's say in presence of anthropogenic climate change, while in light here, these bars, you have what would have been the excess, or let's say the heat-related mortality in a world without climate change. So basically we estimated all this for each of the 700 something locations, and we aggregated by country, and this is what you see here. And eventually, we estimated the difference in terms of excess mortality between these two scenarios. That is basically what you find here. So what we saw overall is that 0.98% of excess mortality, heat-related excess mortality in the counterfactual scenario, and of course, more excess mortality in the factual scenario that is with anthropogenic climate change, that it translates into 101.56%. So the difference between the two, that is basically this number here, is 0.58%. It represents the all-cause mortality that can be attributed to heat induced by anthropogenic climate change. So the idea is that what in a final step, what we did is to kind of rescale this difference over the observed, or let's say the impact or the excess mortality in the anthropogenic climate change, in a way to estimate what is the proportion of the excess mortality happening today that can be attributed to in human-induced climate change. So it's basically what we try to illustrate here, and we found that overall, 37% of heat-related deaths can be attributed to human-induced climate change in this assessment, these locations that we included. And in a later step, what we did is to kind of extrapolate this and compute what would be like the mortality rate attributed to heat-related, or let's say heat-induced climate change. So in here, what we observed is that on average, 2.2 deaths per 100,000 population per year can be attributed to heat induced by human influences, let's say, of climate change. So as you could see in this assessment, it had like very powerful message. It's really, we provide evidence on the clear, or let's say, of the impacts of climate change over health burden that we observe today. And you can see that, of course, this evidence can be very, very useful for, let's say, to support policymaking processes. And more importantly, I think it was about the key message about the relevance of these findings in terms of to put a little bit more attention to what is happening, saying that climate change is not something that will happen in the future. It's already happening today. We can talk about the projections, but we cannot focus on the projections in terms of impacts of climate change. It's really that already we are suffering. So it's really to say, okay, we need to do or put more emphasis in terms of implementing strong mitigation policies to abate this warming in the future, but more importantly, to implement adaptation strategies that would help us to reduce our vulnerability, in this case, for heat. But of course, we had to acknowledge several limitations. And it's true that although it was one of the biggest, let's say, assessment on this field in terms of attribution of health impacts, we know that, for example, it cannot be considered a worldwide study because we focus our assessment on the locations that were included in the MCC. And we know that there are important regions in the world that were not covered. This is an important limitation that we have in our field in environmental epi, because we are very much aware that vulnerability is very heterogeneous and changes from one location to the other. So at some point we can extrapolate risk that we observe in Europe into places like Africa or Asia. So at some point we need better data that would help us to better identify, or let's say assess what is the vulnerability of these locations that currently are unobserved or unexplored. On the other side as well, something that we have to bear in mind, we have to do a simplification in terms of risk. We assume that in a way we didn't account for adaptation, in the sense that we assume a kind of average risk across the 30 years that we assessed. And the idea is that, okay, it's likely, and we know that, as you could see here in this plot, that actually there might have been a partial adaptation of the population to heat. So at some point, we don't know if which impact this could have had, because probably the idea is that probably at the end of the period, the risk might have been lower compared to the beginning. So eventually, as you could see, we had to do a kind of crude simplification. And something as well that we have to bear in mind is that the risk that we apply to both scenarios is the observed risk, that is the one that we estimated in a world with climate change. So we don't know what would have been the risk without climate change. So again, it's very difficult, and I expect that in the future is something that we will implement in this field of climate change epidemiology. And finally, the lack of epidemiological causal basis. This is important because this assessment is purely based on an ecological design, that as most of the climate change epidemiological studies. So at some point, if we want to talk about attribution, we have to improve our way how we can assess causal links in this field. So just as a kind of final wrap up on this topic, and as I said, I really want you to make you fun about this kind of studies. Is first because as we know, it can be a powerful tool for climate change policy, and as well it can help understanding the mechanism by which climate change affects health. It can support refining projections of future health effects of climate change, and as well improve adaptation to climate change impacts and disaster recovery. As well, it can increase motivation for climate mitigation, as I said, just learning about what is happening today and the urgency to really act. And also demonstrate causal links between greenhouse gas emissions and climate change impacts that serve as a basis of evidence underpinning climate-related lawsuits, as I said previously. And finally, what I believe is also very, very attractive is an excellent platform for interdisciplinary research, really to put together experts on different fields, from climate science, working more on the modeling side, climate epidemiologists working on the assessment of health impacts, and at the later stage, other experts in other fields like economy, law, etc., can take part of these investigations. So definitely it's an excellent platform for enlarging our kind of research area, grab information and grasp, knowledge from other fields, and enrich our research portfolio, which I think is also very relevant for young researchers. And just as a final point, something that I think it's also to bear in mind, and as I said, for me, this research field can be considered kind of very powerful research line in the future in climate change epidemiology. Climate attribution is something that has been developed for years in climate science field, but not much in epidemiology. And if we really want to advance in climate litigation, really advance on the fight against climate change, we have to put a value on what is happening in terms of extreme events, in terms of excess deaths, burden, economic cost, etc. And all this can help people change your mind, and as well help, advancing or let's say winning different initiatives in courts, etc. So as important elements that I believe we should focus in the future is first, assess causality, use advanced methods in environmental epidemiology that can help us to clarify causal links. Second point, to provide innovative frameworks that probably, think about if as the World Attribution Initiative, they provided this evidence on the role of climate change. If we can couple this with health impacts, that could be even much more powerful. And finally, we have to think about how we can address this research question in a more broader perspective and provide global estimates that are closer to the, let's say, the real, what is happening today. So yeah, that's all. Thank you very much for your attention. I'm happy to take questions. Thank you.
Thank you, Anna. Thank you for the wonderful presentation. I think you gave us a very clear introduction from climate science, how to detect and attribute extreme weather events, and this type of extreme events attribution to the trend attribution and to the landmark study you have, the MCC colleagues have been working on. So thank you very much. And I think there will be a lot of questions from our audience. So while our online audience is typing your questions in the chat box, we do have already collected some questions from our students. So there are several types of questions that students are particularly interested in. For example, the first type, I think for some of the students, they are wondering, you have given this great example of attributing heat-related mortality. So they are wondering if this type of technique can be used to attribute other extreme weather events like hurricanes or wildfires.
Yeah, exactly. I mean, as I said in this assessment, in this presentation, I focus on heat and health because in a way, I mean, of course, it's a bit biased because it has been my research field for already several years. But we know that within the attribution science, it's not only about heat waves. Actually, there's also a very new report published by this global weather attribution initiative on the floods happening in Central Europe in this summer. Again, estimated that actually the role of climate change was very substantial in, let's say, in increasing the probability of this event. So definitely this kind of framework can be extended to other extreme weather events. Of course, with some caveats and some, limitations, but I believe that if we try to, let's say, it would be easy to adapt this framework to other extreme weather events if data, of course, is available.
Thank you. And I think we have a chat box from our online audience. Exactly the same question some of the students are also asking. So Ben Moni is asking, why is the DIAMP project missing measurements from most of Africa? And also it's kind of related to the question students asking in the multi-country, multi-city test. They said they only have South Africa, doesn't have much of Africa. And also one of our students is asking why there's no data from the South Pacific, where she's have experience living in the small island like Fiji. So why there's no such coverage?
Well, maybe I can give you a little bit of story about how the MCC started. And basically it was, I think in 2014, during a conference that a group of researchers working on climate change, epidemiology, mostly on the temperature-related health impacts, they had an informal meeting and they were discussing the possibility of probably putting together some data from their countries. For example, one have data on temperature mortality in the UK, other had in Japan, the other one had it in Spain. So eventually the idea is that they said, okay, maybe we can start putting all this data together instead of assessing our impacts, or let's say our estimates in our country. It would be nice to compare different locations at the same time, because as I said, the idea of the peculiarity in a way of temperature-related health impacts is that the effect is very dependent on the location. So it's nice to compare these estimates across locations to understand vulnerabilities and potential vulnerability factors. So as I said, it started kind of informal way, and they started, opening the door to other collaborators, colleagues working, and eventually it grew until nowadays that we are around, I think, 70 researchers from 43 countries with all these bunch of locations with different data sets, and also not only focusing on the idea of temperature and mortality, but also air pollution, on projections, in a way, it's a project that greatly grow in an exponential way. But the idea how the beauty of this project, how it's developed and how it started, is that it works in a very informal way, in the sense that the idea how you contribute, you take part of this consortium by providing data on a specific country that is missing, because you had it because of your research or whatever, and it's a project that is not directly funded. It works, let's say, on each funds of each partner. The reason why there are some places in the world that is not, let's say, covered within this project is basically because so far we didn't manage to get data from these locations. And it's a problem, of course, of places like in Africa, where good quality on mortality, daily mortality in specific locations in Africa is very difficult to find, especially because at some point what you need is data that is somehow comparable in terms of quality and temporal scale. And especially this idea that it should be daily mortality, etc. Because the part on them, whether we know that it's relatively easy to get it from reanalysis data, etc. But the main limiting factor here is the mortality data. And that's why, in a way, we didn't manage so far to kind of get this information here in terms of observed mortality in this assessment. However, very recently, as I mentioned in my first slide, we perform a global assessment in which, basically based on information of the observed locations, our colleagues in Monash, they managed to extrapolate the risks in unobserved locations and eventually provide kind of comprehensive assessment on, let's say, non-optimal temperature-related mortality across the globe. I invite you to have a look. It's I think it was recently published in Lancet Planetary Health.
Thanks, Anna. I think you give very good history and also development of MCC, why it's not covered, and what's the most recent advances in predicting the temperature mortality association in places where you don't have mortality data. There are always a lot of questions, but I do have one kind of question like related to your answer. This one student is kind of very astonished about since the heat-related mortality risk varies across places that you have shown in your slides. So the question is, why do like places have even they have similar latitude, maybe even with the same urbanization level, why do they have different heat-related mortality risk?
Well, it's a very good question, and I must say difficult to answer in a very clear way. How we could, in a way, we know that vulnerability to heat, or let's say to non-optimal temperature, depends on a complex network of different factors that are highly interconnected. It's not like we know so far that what makes one city more vulnerable to the other is not because of one unique factor. It's because of combination of different factors that actually are very much dependent between each other. Thinking that, for example, we published, I think it was in 2018, a study was led by our colleague Francesco Serra, in which we tried to assess specifically this, to try to understand what were the contextual factors defined at city level that can give us some hints about which locations are more vulnerable in terms of higher excess mortality due to heat and cold compared to others. And eventually what we saw in this assessment is that it's like not only one factor, it was a combination of probably cities that are more urbanized, but also more unequal, are those with a higher heat-related burden compared to others with a lower level in this case. While for cold, the story was much more complicated with no clear patterns around. But again, the idea how, or let's say the main factors driving this difference is nowadays a very important or very crucial point that we are trying to disentangle, especially because we know that if we understand what are the mechanisms, or let's say the reasons why one city is more resilient compared to other, this can help us to understand which mechanism in terms of adaptation we can apply to other places to try to protect or reduce our vulnerabilities in the future. So hopefully, if you ask me this question in a few years, I hope I will answer this question. But I think right now it's very difficult to say.
Yeah, I think it's an excellent answer. And also, it's kind of related to one online audience questions regarding the difference in the heat-related mortality in urban versus rural and in population of color communities. I think it's more related to Francesca Serra's paper you mentioned.
Yeah, in a way, I mean, it's true that in this assessment, and I must say that in the MCC, most of the locations that we have are cities. So in a way, the risks that we obtain are mostly representative of urban locations. This is one of our limitations in this assessment. And probably if you need to go a kind of national level assessment in which you can better disentangle the different, let's say, patterns in terms of vulnerability to heat and cold in rural versus urban. And as I said, it's a story that needs to, we need to address in the next years. And I know there are initiatives in terms of nationwide assessment, try to see patterns between urban, rural locations, etc.
Yeah, I think kind of the final group of questions students are, and also our online audiences interested in adaptation. So regarding the adaptation measures, students are kind of wondering how most immediate needs to deal with increasing temperature can be balanced against the long-term goals of emission reduction. Basically asking, using adaptation measures to counter, the long-term global warming impacts. So, and also, if there are some studies like this, are there any practical, suggestions on how local communities can do about the adaptation measures?
Yeah, and I must say it was one of the key messages of this assessment that I presented today in this attribution study, because of course it gives a little bit, it gives them the message about the urgency in terms of abating, or let's say reducing the warming in the future. But more importantly, what it's saying is that we really need to reduce our vulnerability, because the idea is that with mitigation, we know that these benefits will come in the next decades, while with adaptation, these benefits can come earlier. And probably this can be even more efficient compared to just waiting for, let's say, the mitigation strategies to have some impacts. And it's true that we have to think about, even in the best of the scenarios today in which we set emissions to zero, we will be anyway exposed to warmer climate in the next decades. So it's about really, again, to put emphasis into the idea of adaptation, that it might be the key in all this story. And with regards to how we can counteract future warming in terms of how much we can decrease our vulnerability to counteract this warming, I know that there have been some initiatives of some studies published in the past. For example, there's a study by our colleagues in UMIA that they estimated what is kind of how much we would need to reduce our vulnerability in the future to reduce, or let's say, to keep our heat-related deaths in the future constant despite the global warming. So in a way, this is a very nice exercise, and it's something that as well I'm leading an initiative within the MCC to try to address this, because as well, this can help us about how much we need to adapt to really do something to have some impacts in terms of reductions of heat-related mortality. Because imagine that if warming continues and let's say the pace at which we adapt is not quick enough, let's say, to kind of counteract this warming, we eventually will have the same heat-related deaths today that in the future, which of course it would be fine, but ideally what we would like is that the heat-related deaths happening today won't happen in the future anyway.
Thank you, Anna. I think I thought Tobias posted a comment. Really fantastic talk. So I think if is there any final question? If there's no final question, thank you, Anna, very much for this really amazing talk. And I think both the students and I'm sure our online audience learned a lot from you. But thank you so much.
Thank you. Thanks a lot for the invitation. A pleasure.